I asked Bernhard to come and talk to us about Aqua because from my perspective, Aqua has the potential to greatly decrease the amount of work that all libp2p folks have to do. When we first started libp2p, I was heavily considering putting a VM into libp2p itself because I didn't want to pay the horrible complexity of having to write an additional protocol per language, per implementation. Because libp2p is a bag of protocols and it encourages a lot of people to create little granular protocols, then when you multiply it out by every single implementation, that gets really painful. Now, the VMs at the time weren't good enough. We didn't have WASM yet. We had V8. And I think the time has come. So Bernhard is going to talk about Aqua, which has some really magical distributed systems programming languages stuff. And I'll help support a little bit. Yeah. So this is the problem, right? So libp2p protocol implementations, there's a lot of protocols, and we want way more. This is, in the libp2p vision, this is 1% of what we would like to see in terms of protocols created. And we have a lot of platforms, and we end up with this grid of for each protocol, you have to write an implementation. And this is just not gonna work, right? And I knew this at the time, at the beginning. It was it's the right way to get started, but not the right way in the long term. Now, enter a VM. If you have a portable way of writing the protocols everywhere, then you can kind of write the core bits that you need in one implementation, and then write all of the other stuff in one portable structure. And so we don't know in the libp2p community what we should do, what VM we should have, whether we should have a VM. This talk is going to start that conversation, and probably over this year we'll run some experiments and see what we could write. And potentially, maybe in the future, some libp2p nodes will run a set of protocols through a VM. Cool. So.
All right, thank you. No pressure, right? So why do you want to? Juan covered most of it. What we believe Aqua can help you do is you write once across these different platforms. You can increase in complexity, and more importantly, how do you do it? So we have this stack. It's called Aquamarine. So basically, Fluence does cloudless compute, and as part of that stack, we have libp2p. We have a general purpose WASM runtime. It's a virtual machine on top of WASM time right now, and on top of that, we have what's called Aqua VM. And Aqua VM is basically the interpreter of the compiled Aqua language, which you would be using to write distributed algorithms. And what it starts, and the stack is, so this is the Aquamarine stack. It's a little bit, it's part of the Fluence cloudless stack, but it's without the economics and any of that. You have Aqua, that's where you specify your business logic. That's where you build your distributed algorithms. You compile it, we have an Aqua compiler. You compile it to AIR. AIR is, it's not bytecode, it's actually a Lisp-like closure. And then you have the Aqua VM. So this is all happening at the developer side. This is the VM, which would be running on Marine or another web WASM runtime we can figure out. And it interprets the AIR to orchestrate locally or choreograph remote functions, whatever this means to you. Down here, this is from our Aqua, we call it Aqua lib, which supports a couple CAD functions. They run on the Fluence reference peer called Nox. And in this particular case, they actually implemented it natively on top of libp2p. And this is the Aqua, this is the function in Rust. And this is the Aqua code that calls this function. And it's literally just a service implementation. A lot of these bindings are literally taken care of for you. And this is important in two aspects, and I'll show you some more examples in a minute. Eventually, at least I believe, and I think Juan believes it, certain algorithms and protocols that are currently implemented natively on libp2p should not be implemented in libp2p. You want to abstract it to a higher level and take advantage of a much more humane programming approach and reusability. However, you don't necessarily want to start this right up front. So with Aqua, you can actually incrementally start experimenting with functionality you already have natively in libp2p and build distributed algorithm and extensions on top of it. So you can start feeling out the boundaries of where this distributed choreography, or if it's local, it's a local orchestration, gets you, and how that improves your interaction with the protocols. So this is sort of a little bit small, sorry. I put too much on it, but These are sort of different algorithms that you can program in Aqua. And the important part is, if you look over here, this is basically, this is a quorum service across multiple peers. The entire topology is resolved for you. You don't have to start figuring out how you get your peers and how you get them together. This is all taken care of for you with at the configuration level of Aqua. And then your peer references literally are on this peer, run this service, which in this particular case goes to a WebAssembly function that's been deployed to potentially a different peer. Could be the same, doesn't have to. This is how you basically would create a cycle balancer, a round robin protocol. 5 lines, you don't have to deal with any of the low level stuff. This is how we resolve subnets. So right now in Fluence, what we're doing is we're basically, when you build cloudless functions, you end up committing to a deal, which gives an on-chain representation. We take this information on-chain and do a single-use network overlay on the peer-to-peer network. So that's how you cut down with, as the network grows, that's how you can cut down on the travel, on the routing. And what we're using Kademlia for in this particular case is literally just the lookup for IP addresses. This is all you have to do to build a subnet like that, assuming you have your configuration of the single-use networks or longer-term networks available to you. Other distributed algorithms we got here is, I wrote a multi-party computation 3-round wrapper on a threshold signature scheme. It doesn't matter. It's a multi-round protocol, and we used a Rust crate. We built our bindings in WebAssembly, which are here, and then with Aqua, across multi-parties. So this is only 2 parties, but it can have many peers. You basically choreograph the entire key generation step of your TSS protocol in essentially like, I don't know, I think it's like what, we take like 40 lines or 50 lines. This is like really cool. And it's amazing how much time it saves if you, anyway.
Can I add something? Yeah. Can you go back to the prior slide? Like, I think Bernhard is kind of like working with such superpowers that he's like glossing over like the magic here. Like, for those of us who've like read a lot of the distributed systems programming languages papers, like what's going on here for Arrow subnet workers, this code is going to execute on a bunch of different machines. And this is just how you program all of those different machines at the same time. And so it's a distributed systems programming language, like that then is bound directly into WASM and is libp2p and then runs on native libp2p, right? So you can implement Kademlia instead of like having to reason about a lot like code and how it would work and thinking about it from the perspective of every single node. You can just take the perspective of the whole network at a time, and you program once, and you kind of select where you are, and you can kind of like check in what node you're in and what you should be doing based on that. But you have one program, and it's kind of like relatively easy to like reason about, much easier than like kind of all the pieces, right? It's kind of like the difference between event loop programming and programming with like an async IO type keyword, right? It's like that same kind of programming model difference, but now instead of like dealing with just asynchrony, you're now dealing with like tons of machines at the same time. And so like that becomes like super powerful. And so I think like a lot of the libp2p protocols, like other DHTs and pub/sub things and whatnot, could all be built with this kind of thing, just riding on top of like a very core WASM powered libp2p.
Sorry, I forgot the most important part. So I just wanted to, just real quickly, so Dmitry Kurinsky, who is the CTO of Fluence and one of the co-founders, he's also the inventor, designer, and core implementer of Aqua, the language. And he's currently working on some really cool features, including promises. And so this is really early. This is like happening as we speak. This repo is getting updated. And yield at the topology level. So you take this entire network and you just approach it just like it did in the subnet resolution. And now you can start building a massively improved handling of timeout, which is our fallback for everything in distributed system, into, just from a logical perspective, much easier to understand, group, and maintain over the network without actually having to commit to particular aspects of the network at any given time. You should check it out. I mean, everything's open source. You should look at it. It's really, really interesting. It's really going to push Aqua's capabilities way beyond what they are today, which are actually pretty good, and brings you that much closer to that vision of implementing core protocols at a higher level of abstraction. And that's you.
Yeah, so potentially, if we experiment with this sort of stuff and we can like take one implementation and then try to like jam the Aqua VM and Marine VM on top of it, then we can try writing some of these protocols in Aqua and then try running it. And we can end up with an environment where you just write the protocol once and then it runs everywhere. Now, of course, sometimes you'll encounter things that are like not performant enough. And then at that point, you should decide, okay, great, I'm going to implement it natively in that language. But then, ideally, we could solve the problem of like the combinatorics nightmare of that libp2p currently has with an approach like this, where by default, there's always one implementation. Maybe it's the most performant. Maybe it's not. And if it's not, then you like go out into like your own thing. Now, the big problem with this is like putting a VM in the networking stack sounds a little scary, right? Like putting a VM in the networking stack is like, question marks there. Although I guess a lot of Linux things these days have VMs, so in the networking stack, so maybe it's fine. Yeah, Adin?
If you decide you want to go down to the native layer, or like you want to write a spec that's like how to do this, can you write the spec without the Aqua and the Marine specs?
Yes. Yes. So at least me thinking about it, you would implement it natively. And then if you wanted to run it as part of Aqua, what you do is you write this WebAssembly wrapper, basically API representation of your native function, and then bring that back up into Aqua. So if you have different optimization requirements across different stacks, the only thing that changes is not the topology or the topology logic, it's the implementation of the WebAssembly that binds your native implementation to the distributed algorithm at the Aqua level. And this is what I meant incrementally. You can start doing these experimentations without fully committing of re-implementing algorithms, which I think is the way to experiment.
I don't know if you were also hinting at this, but there's also a question of like, when do you write the spec? How do you write the spec of the protocol? And then how do you go from spec of the protocol to implementations and whatnot? Now with like the pervasive VM world and that we have LLMs, you could come up with like a distributed systems programming language type thing that is very human oriented, where you just specify the thing. And from that, compile out a TLA plus spec to verify that the protocol is actually correct. And then from that, compile out like the thing that could run in a VM like this. And then from that, compile out like the native thing if you really need it. And so I think like that's where like things are going to head in the kind of like 5-10 year time scale. And so we could be in a world where like we're writing libp2p specs that themselves are define the code that gets executed and run in most cases or in a lot of cases, except for when like you have to dig into the machine and like fix something because the LLM didn't get it right.